Hello everyone, my name is Hsueh-Hung. I come from National Taiwan University. Today's my topic is identifying tomato diseases from leaf images using deep convolutional neural networks. Let's start to talk about tomato. Tomato is an important food in our daily life. It has plentiful different nutrition. Actually, it has the most vitamin C in all kinds of vegetables. You just need to consume 2 tomatoes a day, and you can get sufficient amount of vitamin C. Just like what you can see in this chart, tomato also contain many different kinds of vitamins and minerals. And also, tomato had antioxidant content, which can help people to prevent cancer. Due to this advantage, tomato is planted and consumed worldwide, and Taiwan is not an exception. So next, let me talk about tomato planting in Taiwan. In 2019, 40 million square meter field were used to plant tomato in Taiwan, and 100 million kilogram tomatoes were produced. And the output value of this tomato was about 4 billion NT dollars. Hence, tomato is a very important economic product in Taiwan's farmers. However, the plant pathogens have a tremendous impact on tomato production. In a research at 2006 says that plant pathogens cause up to 16% estimate potential yield loss globally. To Taiwan's tomato farmers, the loss will be about 600 million NT dollars each year. It is not a small amount of money. So in order to reduce the loss, it is essential for farmers to deal with the problem of pathogens. But before we start to solve the problem, let's take some time to know what kind of disease we have to face. So let's talk about tomato diseases. Here's a chart of tomato diseases. There are 11 different tomato diseases in this chart. In some disease, the lesions of same disease at different stage, they may look very different. So in this research, we try to identify 8 categories, and each categories are disease of very similar symptoms. Okay, so next, let's back to talk about how to identify the diseases. Conventionally, the identification of plant diseases relied on experienced farmer or disease experts' naked eye observation. But there are some problems. First, maybe the farmer is not an experienced farmer, and he will make a wrong decision, use a wrong pesticide, and make things get worse. Or the farmer will ask disease expert for help, but this will cause another problem called disease expert labor, and maybe let them make error. So if we want to avoid the human error and reduce the disease expert's labor, we need to develop an identification system. And this system will be non-destructive, convenient, and with high accuracy. So here is the architecture of the system. It consists of front end and the back end. And the back end is the tomato disease identification models. By using this system, the user can easily use their smartphone to take a picture of diseased tomato images. And our system can identify the disease and get some treatment suggestions. And in this study, we will focus on talk about tomato disease identification models, the back end. Okay, let's start to introduce the model first. Here are 2 different models, anomaly detection model and disease identification models. The anomaly detection model is used to make sure the user send in a detectable image. And next, the purpose of disease identification model is clear. It is used to identify disease images. And let's start with anomaly detection model first. Okay, so let's talk more about why we need an anomaly detection model. Because we hope the user can input a clear and focused image of diseased tomato leaves like the image at the right side. However, if user input an image like the image at the left side, it will cause a worse identification result, and we want to prevent this situation. Hence, we need to develop an anomaly detection model to prevent user input some strange image, and this is the reason why we need this kind of model. Okay, next, we have the flow of anomaly detection model. There is a VG16 models and isolation forest. The input is one leaf image. The VG16 will give you a feature vector of 1,000 entries. So now, think about the vector with thousands entries of anomalous images. It would look very different from normal images. So you can think that in the feature space, the anomalous image in that space would be outlier. So that would be far away from the center of normal leaf image in the space. And this is the principle how we find and identify anomalous image using our anomaly detection model. And next, here is my image dataset for training and testing the anomaly detection models. The normal image and the anomalous image also shows in this page. Okay, next, this is the result of trained anomaly detection models. The mean accuracy was about 98%. After introduce the anomaly detection models, let's introduce disease identification models. In this research, we choose Yellow V4 as our object detection model. Yellow V4 was similar to Yellow V3. However, Yellow V4 had many tricks from other papers to increase the performance. For example, the backbone was CSP.NET 53, and it was a powerful backbone. It had a better performance than ResNet. And the SPP, spatial pyramid pooling, and PAN architectures could make the model had better performance on different scale object detection. And the Yellowhead, this power was same as Yellow V3, and it was used to doing class prediction and bounding box regression. So when we input a leaf image with lesions, we hope the Yellow V4 can help us to find out the location and the class of the lesions. And here, I will talk about the images that will be used to train the model. There were 8 different categories of tomato disease. There were specks, scorch and spots with yellow halos, yellow spots, ring spots, water soaked lesions, powdery mildew, systemic disorders, and serpentine mines. And these images were all collected at tomato fields in Taiwan by plant pathologists. Next is the data preparation. The lesion in this image will be labeled using Label Image Toolkit, and the table shows the number of image and bounding box of 8 categories, and the ratio of training data and test data is about 4:1. And here is the training details. The page size was 64. The image size was 416 by 416. The epochs was 100. The SGD was used to be an optimizer, and the initial learning rate was 0.0015. And the GPU used to train the model was NVIDIA Titan RTX. After finished training, we need to do some evaluation. First, we need to choose the best confidence score threshold to use in the model. What is confidence threshold? It is a threshold to let model decide to preserve or discard a detection. In other words, when model detect an object with a confidence score higher than threshold, and the model will preserve this detection. And if lower than the threshold, the model will discard this detection. And here we use F1 score to choose the threshold. F1 score can give a balanced evaluation to precision and recall. And 0.4 was chosen as the threshold to test this model. Next, we use 0.4 as the threshold to evaluate the model's performance. And the mean average precision was 77.27%. Okay, here are some successful dictation images. As you can see, the model can find the lesion in the image of 8 different categories. Okay, here's another successful dictation example. As you can see, the model can find the lesion of different categories in one image. And here is a misdetection image. In these images, we can find there are 2 ground truth bounding boxes, the green one, but the model only detects one of them. And next, this is another example. And this is the same situation. The model misdetection one object in the image. Okay, here's my conclusion. A model achieved a mean accuracy of 98.0% in anomaly detection, and the model achieved a mean average precision of 77.27% in identifying 8 categories. Okay, here's the future works. First, I want to balance the data set and collect more images. And next, I want to optimize the YOLO-V4 models using the new data set. And then I want to reduce the misdetection cases. And in the end, I want to develop a chatbot to work with the identification service. In this research, I want to thank to Taiwan Agricultural Research Institute for collecting and providing all of these images. Thanks for your attention.